Okay, in class today, covering up for the class that did not happen last Thursday, I want to speak about the minimum weight vertex cover problem. I want to show how we can solve it using integer linear programming, ILP. I want to show how we can solve it much faster, even though we will not get the exact solution, but something that is approximation of the solution. We will be able, however, to prove that what we will get fast will be a true approximation. Namely, it will cost no more than twice the optimum solution, but still we will live long enough to see actually the algorithm terminates in this case. And for this, we will see how linear programming, not the integer linear programming, but linear programming directly can be used. And after that, we will go back to the unweighted vertex cover problem, and we'll see that not all algorithms have to be complicated, that actually the weighted, the minimum cardinality vertex cover can be solved very easily and very fast with the same level of approximation, giving a factor 2 approximation, not more than twice. So, what is the weighted vertex cover problem? First, I want to tell you what is a vertex cover. I'm given a graph, and I want to generate a subset of vertices such that each and every edge in the edges of the graph has at least one of its endpoints in the cover. Otherwise, I don't just say this set of vertices is not a cover. So I need to pick a subset of vertices such that no matter which edge of the graph I'll look at least one of its endpoints must be in the cover. In this case, I'm covering all the edges of the graph using some set of vertices. For example, I can pick each and every vertex of the graph, and that's definitely a cover. However, in the minimum weighted vertex cover, I'll also assume that every vertex vi is given with some cost or weight wi affiliated with this vertex. For example, v4 will cost $8, v1 will cost $3, and so on. I'll denote by wc, namely the cost of the cover, is defined as the sum of cost of the individual vertices in the cover, and we look for the cover which cost as little as possible, obviously. Example, if as I said, I can take all the vertices to be in the cover, and then every edge is very nicely covered, but it will cost 3 plus 3 plus 3 plus 8 plus 9 plus 4. Or I can pick a much cheaper cover by taking only v6 and v4 to be in the cover. I'll claim that this is the optimum cover, so I'll denote it as C-opt. It will consist of the vertices v4 and v6, and the cost of this cover will be $4 plus $8 plus $4, making it $12. Had I not used v4 in the cover, I still need to pick the edge v1, v4, so I would have to use v1. Similarly, I'd have to use v2 and v3, paying altogether for the three of them $9 instead of the $8 that I'm paying for v8. Now, the minimum cardinality or the minimum weight vertex cover are both NP hard. We cannot really hope to see the solution if the problem is very large. Just unless, of course, P equals NP if you want to believe in it, but most people don't. So if P is not NP, we probably don't have an algorithm that always runs fast, no matter what the input is, but we'll get somehow close to it. Minimum cardinality, by the way, I did not define it. It's just the cover that has as few vertices as possible. That is, I'll assume that the cost of every vertex is $1, so I'm just minimizing uniform costs. Okay, let's denote the ILP for this problem. It's also a good opportunity to practice a bit how to use vector notation. So the variables that I'm going to use will be one variable per each one of the vertices. For the vertex v1, I'll denote a variable, an unknown, called x1, and for the last vertex over here, probably v6, I'll say that x6 is the last variable. The list of all these variables I'll denote by x vector, borrowing the arrow notation above the x, that is x with arrow above it means the list of all the vectors x1 dot 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 xn. And how are these variables are related to the vertex cover problem is very simple. I'll force each one of them to be a Boolean variable, somewhere between that is either 0 or 1. The way I'll say it is by requiring it to be both an integer and between 0 and 1. And if xi is 1, I'll understand that vi has to be in the cover. If xi is 0, then vi is not in the cover. So the vertices in the subgraph that you see above would probably be if our vertices are v1, v2, v3, v4, v5. For the graph that appears in the slide, ignore everything that you see here. It's waiting for us for the second part of the class. If these are my set of variables, then x for the optimum cover would be 0, 0, 0, v5 and v6, then 0, 1, 0, and 1, and this will actually be the what will appear in a second as x vector opt, the optimum cover in this case. So only v4 and v6 are in the cover, so that's why they're x sub 4. That's why x sub 4 and x sub 6 are both 1, while xi for every other vertex, they are all zeros. So, and let w vector, again, list of numbers, be just the list of a cost of weights of each one of the vertices: $3, $3, $3, 8, 9, and 4. And let's see the ILP. So the cost function is, of course, to minimize the sum of the sum of the cost of the vertices that we are using. So mathematically, we'll write it as sum up all the weights of each one of the vertices times, are we taking it, namely xi is 1, or are we avoid taking it, namely xi is 0. In vector notation, using the dot product, this is just w dot product x, w vector dot product x vector, that is w1 times x1 plus dot 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 w6 times x6 in this graph. Now, and of course, we would like to find values of xi's with 0 and 1, such that the sum is as small as possible, such that, and now I'm going to express how my set of vertices needs to be a cover. namely for each one of the edges in the graph, every edge say v1, v4, I'll claim that xi plus xj, x1 plus x4 must be larger or equal than 1. That is, either x1 is in the cover, or x4 is in the cover, or both are in the cover. Even better. However, I will not accept any solutions for which both xi and xj are 0, because then the edge vi, vj is not covered. None of its endpoint is in the cover. And now I need to tell the ILP to make sure that every xi is a Boolean variable, so I'll constrain xi to be between 0 and 1. So far it's linear constraints for each one of the xi's. And in the ILP problem, we will require that every xi is, of course, an integer. And since it's an integer and between 0 and 1, then it's either 0 or 1. However, we are going to see that we also look at the LP version of this problem, the linear programming version of this problem, at which we don't make this requirement that the xi's are integers. They can be anything, namely a float values is absolutely fine. Okay, and we'll see that there is a good motivation to solve the problem using linear programming instead of integer linear programming. And as I mentioned about linear programming, it's extremely hard to find a linear programming problem that runs slow. Simplex algorithm in general, the classical algorithm that solves linear programming, in almost every instance runs extremely fast, even for huge graphs, even for huge number of constraints, and it's very unlikely to hit accidentally an input that will cause the linear programming to run slow. So we'll just say if we can phrase it as linear programming, then if we phrase it as linear programming, then it will run fast. But who told us that it's related to something, right? We already saw in last class that the solution for the linear programming is not necessarily consist of zeros and one. Going back to the slides, going back to the slides, we already talked about the problem that involved the following graph, right? Said here is my graph, consists of v1, v2, v3, and if I'll run the linear programming in this case, unweighted case, or the weight of every vertex is 1, and I'll have 3 vertices, x1, x2, and x3, and I'm trying to minimize x1 plus x2 plus x3 such that, okay, we will have to go back to this later, x1 such that x1 plus x2 is larger or equal than 1, x1 plus x3 larger or equal than 1, and x1, a2 plus x3 is larger or equal than 1. And as we saw, the solution in this case is x1 equals x2 equals x3 equals half for each one of the variables. This is the optimum solution of this problem, and it's just to demonstrate that we are not guaranteed at all that our solution for the linear programming will be an integer. Okay, so we need to see that this solution helps us in some way, and for this I just need a few notation. I'll write x vector with f for float as the list of values x1 dot 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 xn, x1 f all the way up to xn f. This is just a solution that I am obtaining for the linear programming, not the integer linear programming, for the linear programming. X optimum vector x1 dot 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 xn, this will be the solution for the integer linear programming. That's a global optimum. I cannot do any better than this, provided that all the xi's are integers which are between 0 and 1. And based on the way I wrote the ILP, X optimum is the optimum solution for the weighted vertex cover. Okay, and C optimum is just a set of vertices that corresponds to X optimum. Remember, X optimum is a list of zeros and ones, and C optimum is a list of vertices. Finally, X approximate is a new vector that I'm going to define. We saw it in the last class. X approximate will be x1 approximate, x2 approximate, dot 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 xn approximate. This is going to be an approximate solution which consists of integers, only integers. And how do I generate these integers? If xi, if the solution for the linear programming xif is smaller than half, then xi approximated is rounded down, truncated to be 0. And in this case, I will not place the vertex vi in the approximated vertex cover. However, if xif is larger or equal than 0, then xi approximated is rounded up, rounded to be 1, and in this case vi will be in the optimum solution, in the approximated solution. The approximated will be in the approximated solution. So in this example that we just drew, x1 approximate equals x2 approximate equals x3 approximate equals 1, and the vertex cover that I'll generate for the approximate will be v1, v2, v3. You're taking all the vertices, even though it's clear that taking any pair of vertices would be enough. So I'm definitely overkilling here. Okay, now let's see that what I'm calling C approximate, C4 cover, is actually a vertex cover at all. Who told me that it's vertex cover? I want to convince you that X approximate, or the corresponding C approximate, is indeed a vertex cover. And the reason is very simple. Look at any one of the edges, Vi, Vj, in the graph. Look at any one of the edges, Vi, Vj. You solve the linear programming, not the ILP, but the LP. Solve the linear programming, meaning that for any one of the edges, xi plus xj, two endpoints of the vertices, are larger or equal than 1, meaning that either xi is at least half or xj is at least half, or both, of course. Because if xi is smaller than half and xj is smaller than half, then their sum will be smaller than 1, obviously. So by looking at X approximate or C approximate accordingly, our solution is a linear, our solution is indeed a vertex cover. That's good. So I still didn't tell you why I think that it's a good approximation, but at least it is a vertex cover no matter what. Okay, finally, second claim will be that I'm comparing the cost of the linear programming, not the ILP. This is a cost. This is what I'm getting from the solution to the cost function when I'm looking at the float vectors of zeros and one, the vector in the example behind me, the example of the half, half, half of the three vertices. I'm looking at the cost of x dot product with a vector of weights. These are just the sums of weights. This is what the linear programming trying to optimize. And I want to convince you that this is small or equal than the same weight vector times the optimum solution. And that sounds very strange. If this is the optimum solution, how come I can find a solution that is smaller than that? Well, it's the optimum solution. It is the smallest that you can get if you guarantee that all the xi's are integers, or between 0 and 1s. You either take a vertex or not. Here, in the float problem, in the linear programming, you allowed vertices to be smaller than, you allowed xi's to be anything between 0 and 1, including floats. So w times xf, the cost that you're paying right here, for the linear programming is smaller than the corresponding cost of the integer linear programming. In the integer linear programming, you added more constraints, so your minimum, of course, if you're adding more constraints, then your minimum solution becomes more and more expensive. So that's the cost that we are paying as a solution for the linear programming. This is the cost that we are paying for the integer linear programming. Now let's put it all together. Look at the cost of the approximated solution, but we just created as the approximated solution. In the approximated solution, what I paid is how did I generate the approximated solution from the float solution? I took every element of the float solution and I added something, but I added something only if this number is already larger. Only if this number is already larger than half, then I made it 1. I'll never multiply xi by 3. I'll never multiply x5 by 5. I'll only increase the xi's only if they are already larger than half. Only then I'll replace their value with 1. So for each one of the xi's, the way I moved from the float solution to the approximated solution was by increasing its value by something which is less than 2. And for other xi's, I even decrease them to be 0. But even if I ignore the ones that I decreased, only concentrate on the ones that I increase them by at most 2. So w times x approximated is smaller or equal than 2 times w times the float solution. And what did we just say about w times the float solution? It is smaller or equal than w times the optimum solution. So taking these two to the next condition, these two just came from here, and we are getting that w times the approximated solution is no more than w times the optimum solution. In other words, the approximated cost is at most twice the optimum solution that you can get. And to do it, what did we do algorithmically? We were solving a linear programming, not a very slow integer linear programming, but a linear programming, and round the values that we are getting up or down, and that tells us which solution we take. So it's very, very fast process altogether, but we do need the use of linear programming. Also worth mentioning that what we are getting is a 2 approximation, called a solution that is not optimum, but no more than twice the optimum. We'll shorthand it or abbreviate it to say it's 2 approximation of the weighted vertex cover problem. Okay, so let's see what did we study about the vertex cover problem, we saw a two approximation for the linear programming for the unweighted case. Unweighted case, the cost of every vertex is 1, or there is no weights at all, and we just look at the cardinality. We did see that same type of argument gave us a factor 2 approximation, a 2 approximation using the linear programming. We then saw that the solution via the linear programming can be extended to the weighted case, and that was pretty cool that we use the linear programming in the weighted case. And finally, because we're already here, I want to show you that not all algorithms needs to be complicated. Not everything needs to go through linear programming. If I was wondering, or one might wonder, can we solve the unweighted problem without going through through linear programming? Because linear programming, we need a simplex library. It still takes more time to understand and to implement, and yada yada. Let's see if there is a really simple solution that will give us the same guarantee on the approximation. And indeed, here is Bar Yehuda's algorithm that suggests a factor 2 approximation. It is an approximation with the same level of quality, but in much smaller effort. So now I need a new algorithm, a new graph. So here are my vertices, v1, v2, v3, etc., v5, v6. Here is a new graph. Now I don't have any weights of the to the vertices. They all equally costly. And I want to generate a vertex cover. Again, I want to generate a set C approximate, which will be a vertex cover. Namely, every edge will contain a vertex in the approximated vertex cover. And I'll want to argue that this set C approximate that I will take when I'll consider, if I look at the cardinality, how many vertices did I take in my approximated solution? This will be, of course, larger or equal than C optimum. How many vertices will I take if I run, say, the integer linear programming, or just find the best solution to the problem? So approximated solution, since we are trying to minimize, of course, larger or equal than the optimum solution. However, it is not much larger. It will be less than 2 times C optimum. I will not pay more than twice the optimum. And see how this algorithm works. So, vertex cover approximation for the graph G. The output would be a vertex cover C of this graph. And I'll start when C is empty. C approx, when I'll start, will be the empty set. And the algorithm says pick all the edges in the set age. So right now, age is nothing but E. I'm looking at all the edges of the graph, at all the edges of the graph. And I'll pick an edge that is not covered yet. Edge are the edges that are not covered yet. Not yet covered. And so far, of course, since C is empty, nothing is covered, and I'll pick one. So here are all the edges that are not covered, and I'll pick one of the edges. Say I'm thinking about the edge V1, V2. And the algorithm tells you pick this edge V1, V2 and add to C both vertices U and V. That is, right now, C, instead of being empty, C approximate consists of V1, V2. This is my vertex so far. And now the algorithm tells you delete from edge all the edges that are now covered by V1, V2. I picked V1 and V2. How did I pick this edge is completely irrelevant. It doesn't matter how you decided to pick this edge. Any one of the edges will do for the algorithm. Which of the two vertices will I pick to be in the approximated solution? Both. That's important. I have to use both V1 and V2 and put them in edge. And by doing so, I'm covering some of the edges of the graph. So right now, I'll remove from my graph, I'll remove from edge all the edges that are covered so far. And so what you see over here are the edges that are not covered. Edge are the edges, yet edge are the edges which are not yet covered, which consist only of these four edges. Everything else has been covered. And what's the intuition so far? There is some optimum solution. In the optimum solution, the edge V1, V2 must be covered. Either V1 or V2 are in the optimum solution. What do I do instead? I take both vertices to be in the optimum solution. Instead of thinking which one should I pick, I'll just take both. One of them must be the correct one, and one I am using even though I don't have to. Let's continue with this process. I'll pick yet another edge. Let's say that the next edge that I pick is V1, V5, V6. Let's use the edge V5, V6 to be in the cover. And once again, add to C the both endpoints, add to C to the cover both endpoints of this edge, both V5 and V6. So now C approx consists of V1, V2, V5, and V6. And remove from edge all the edges that are not covered by these red vertices. So what's left of edge? Only the edge V3 and V4. And in the next iteration, I'm doomed to pick this edge, and we'll pick V3 and V4 to the cover. So now my cover consists of the edges V1, V2, V5, V6, and V3, V4. And the argument is that C approximate is not worse than twice the optimum. Let's get back to the slide. At every iteration, I picked an edge arbitrarily. I added both u and v to the cover, both its endpoint of the edge, and I removed from edge, the set of uncovered edges, everything that I just covered, every edge that is adjacent to either u or to v. And of course, the edge uv is one of these edges. Instead, sorry, to v or to w in this case. And we are done with when edge contains no more edges. The moment that a edge is becoming empty, then we are done. And I want to convince you that this is a factor 2 approximation. It is a number of vertices that I used in my optimum solution is at most twice number of vertices that I used in my in the optimum cover is at most twice the optimum solution. And the argument is so simple. Just say, look at every vertex in the optimum solution. You could have used only this vertex. Instead, you are using 2 vertices to be in C. Make sense? Instead of, if you would have been, when you picked the edge VW, had you been very clever, then you could have used either U or V, but not necessarily both to be in the cover. Instead, we are using both. However, the optimum is definitely use either U or V, because otherwise we don't know if neither U nor V are in the optimum cover, then the edge UV is not covered, implying that our optimum cover doesn't work. So for every vertex in the opt, we are taking 2 vertices to be in C. Hence, the cardinality of C is at most twice the cardinality of the optimum. Okay, in other words, C is a 2 approximation of the optimum solution, and we didn't need linear programming, and the running time is just linear in the number of edges and the number of vertices, and usually the number of vertices is smaller than the number of edges. QED, a cute example of approximation algorithm, a cute example of linear programming that we saw earlier, and a cute example of integer linear programming. Thanks, everybody.